Yeah. Hello, we're ready to begin.
Hi.
Hello.
Can you hear me?
Yes, we can.
Okay. Yeah. Hi, Taro. I see you. Hi, Ted. Sorry. Okay.
I reckon.
But she can see us, she says.
Yeah, I think you need to put.
Oh, the back of the head.
I was sharing my screen, but I can stop sharing it.
Yes, we can see. We can see you sharing the screen.
Yes. Would you like me to stop sharing it? Or...
Yes, please. And if you can introduce the session, please.
Yes. So, are you showing the presentation that I sent?
Now we can see you.
Yes. And I can see a presentation. Okay. Right. Okay, yeah, thanks everyone for being here. I am really sorry I can't be there. Unfortunately, various airports and train lines were having travel disruptions, so it made it impossible for me to be there in person. But yeah, please bear with me. So, okay, so this session is going to be on physical climate storylines. We are...
Yeah, we know. Yeah, at the moment.
Sorry, the presentation went away.
Sorry, we'll show you this. Okay. Yeah, so at the moment we can't see the slides. We can only see you.
Yes, because I'm not sharing my screen because you were showing, I think yeah. Should I share my screen or not?
Yes, please.
Okay. Okay, so I was closing this. Okay, so you should see it now.
Yes, we can.
Okay, perfect. Okay, so welcome to the session on physical climate storylines. So as many of you might be aware, physical climate storyline is a methodology that has been developing in the last, well, like let's say about like 8 years or so, like since it's like sort of initial like explicit formulations, but it has a bit of a longer history. But so this is an approach that has been developed mostly to address climate risks among other issues related and is a sort of reaction or novel approach to interpreting climate model output and the use of model projections to both extract information about possible and plausible future climate and explore uncertainty. So the way that physical climate storylines are defined in the IPCC and here are as physically self-consistent unfolding of past events or plausible future events. And sometimes they're also couched in the present. So this session is sort of comes out of some research that has been going on in this project called RECEIT. This is a European Horizon 2020 project that spans across various institutions. I have put the link to the project webpage there, and it is a project that looks at how we can develop physical climate storylines to explore remote impacts of climate hazards on Europe. So how do impacts on sort of remote regions affect sort of socioeconomic conditions over Europe? And we're lucky that some of our presenters today are part of this project. So you will be able to see some of the work that we have been doing in this context. So here we have our program for today. We have 4 oral presentations, and I will also ask, hopefully Sandra is in the audience, I will also ask Sandra to come and maybe give a few minutes sort of overview of her poster that you will be able to see later on and online. So the first talk is going to be by Enrique Gular. Enrique is a researcher at Deltares and a PhD student at the Water and Climate Risk Group at Vrije Universiteit Amsterdam. He's a member of RECEIT, and his PhD is aimed at developing physical climate storylines using physical and statistical models to explore and understand the climatic components of extreme events and climate change trends. So his presentation is going to be on storylines of weather-induced shocks to the soybean supply chain under climate change and different socioeconomic policy. The second talk will be by Taro Kunimitsu. Taro has a PhD in physics from the University of Tokyo, where he was working on early universe cosmology. He also has an additional master's degree in public policy from the University of Chicago, where he has focused on environmental economics and machine learning. His experience is as policy practitioner in the Japanese government, where he worked on science policy, energy policy, culture policy, and education policy. He is now also a member of RECEIT, and he is based at Cicero at the Center for International Climate Research in Oslo, Norway. Our third talk is from Nina Pirtioja from the Finnish Environment Institute. She is a researcher in the climate change program since 2009. She has an MSc in geography from the University of Oulu and a PhD from the Faculty of Agriculture and Forestry from the University of Helsinki. Her PhD was on sensitivity of cereal yields to climate change, estimating the risks and exploring adaptation. Her research is focused on studying approaches to assessing climate change and different risks in different sectors, and applying impact models, indicator analysis, scenarios, and storylines. She has mostly worked with crop models and the agricultural sector, but has since the PhD expanded to also the health sector. And her presentation is going to be about exploring methods of co-creating climate change and impact storylines to complement SSP-based scenarios for informing regional adaptation planning. Our third and invited talk is by Professor Ted Shepard. He is a professor of climate change science at the University of Reading, and the Grantham Professor of Climate Change Science at the University of Reading, and since March 2022 holds a part-time appointment at the Jülich Supercomputing Center in Germany. He's a specialist in large-scale atmospheric dynamics and circulation and its role in climate change, including extreme events, and has published over 200 peer-reviewed articles on atmospheric and climate science. Ted has held leadership roles in international scientific assessments of climate, like the IPCC, and stratospheric ozone as part of the WMO UNEP projects, and in the World Climate Research Program. He has co-authored the US National Academy of Science report on extreme weather event and climate change attribution in 2016, served on the peer review panel for UKCP 18 that are UK national scenarios, climate change scenario, and chaired the science review group at the Met Office Hadley Center from 2017 to 2021. He was elected a fellow of the Royal Society in 2016 and held ERC Advanced Grant from 2014 to 2020. So Ted's research has pioneered the storyline approach to representing deep uncertainty in aspects of climate change related to atmospheric circulation, including extreme events. This has motivated him to begin engaging with stakeholders, for example, on issues such as drought risks and interdisciplinary collaborations with philosophers of science, psychologists, and anthropologists. He is currently a co-chair of the World Climate Research Program's new lighthouse activity called My Climate Risk. And today his presentation is going to be on physical climate storylines, not just those stories. And finally, we have Sandra Ricard from the Politecnico di Milano. She is going to present a poster on the Triple Loop survey to delve into physical climate storylines and address climate risk assessment, learning from farmers' perspectives and behaviors in northern Italy. Sandra is a human environment geographer. She's currently a Marie Curie Action postdoctoral research at the Environmental Intelligence for Global Change Lab at the Department of Electronics, Information and Bioengineering at the Politecnico di Milano. She received her bachelor's degree in geography, a master's in environmental sciences from the University of Girona in Spain, and a PhD in environmental sciences and sustainability at the same institution. Her research include the management and governance of water resources in socio-ecological systems and farmers' behaviors regarding climate change impacts and adaptive capacity through social learning approaches and system dynamics. Sandra co-authored more than 30 publications in World of Science and Scopus journals, attended about 50 national and international conferences, and participated in several international and national research projects while collaborating with universities and research centers from Spain, Netherlands, and New Zealand. Since 2017, she's a lecturer at the Masters in Planning and Management of Natural Risks at the University of Alicante. So we are very lucky to have this great group of presenters. And we have about 20 minutes, like 15 minutes for each presentation, and a short Q&A for clarificatory question. And then we hope to have a bit of a general discussion about lessons learned from applying this new approach. So I have added these questions also in the discussion document in the IIASA Connect platform. So please feel free to make notes about it on that document, but we can come back to it after the presentation when we look at what are the lessons learned from the applications of the storyline approach. How does this differ from the standard approach to assessing climate risks? What have been some of the major barriers that, for example, our speakers, I want to ask them for implementing and applying this approach, and what are the major lessons learned from the presentations that we will see at this forum. So finally, yes, I'm Marina Ballistero-Pacchetti. I'm based at the University of Leeds, and here are my contact details. You can find them also on my profile on the IIASA Connect platform. And yes, I'll stop sharing now, and I hope that, yes, Enrique can come and take it away with the first presentation.
Should I stay here or should I sit here? Can you hear? Okay. Perfect. Even though I prefer this one, but okay. Does this one work as well? No, okay, then I'll have to hold the mic. Hello, everybody. My name is Enrique. Together with Esther, Karin, Christian, and Bart, I'd like to present our work on storylines for soybean in the climate change and socioeconomic scenarios. So soybeans are one of the most important crops in the world. They are specifically used as feed for livestock, so most of the cattle, porks, chicken, most of the meat that we have in the world consume soybeans as the main protein source. And they are also widely used as a vegetable oil and also in many human cultures. Okay. And because of this, the EU is very dependent on soybeans, but there is an interesting fact that is not directly consumption, but rather indirect consumption through the use of soybeans as livestock feed for animals. And the thing is, the EU produces no soybean whatsoever, which renders this interesting situation where it has to import almost 100% of what it consumes in Europe. And also interesting, the vast majority of the production of soybeans happens actually in the Americas, more specifically in the United States, in Brazil, and Argentina. And as you can see here, the quality is not that good, but yeah, it's all over those three countries, rendering a very interesting spatial analysis of what could happen in those regions and how it can affect the rest of the soybean supply chain. And that's precisely what we do here. So we first isolate those three countries that represent over 80% of the global soybean production. Then we first find a link between the weather conditions in those regions with the yearly soybean variation. So basically, good weather, bad weather, how does it connect with the soybean yields in each location? And then we process those outputs via the GloBion model done here in IIASA. And finally, with this model, we can transfer the yield variation or the production variation into imports into the EU, and finally into socioeconomic metrics that I'll explain later a bit better what they are. So, and with this pipeline ready, we look at the future and we try to understand what is the risk, what are the impacts of those shocks, so those weather shocks in the producing regions affecting the EU, especially in terms of meat prices and soybean prices and the consumption of those two things, because that's how this pipeline works. So just to be a bit more technical here, one of the main components of our storyline is the hybrid model. That is something that I developed last year here in IIASA together with Esther and Chris. Basically, the hybrid model consists in taking a process-based model, the EPIC IIASA, and we correct it and we improve its performance by merging it with exogenous statistical information, weather information in the location. And to do this, we use specific type of deep neural network that is able to distribute weights and make sure that whatever is happening in each grid location has a higher accuracy than it would have in the original model. And actually, the result is very satisfactory. So we just train this model, and then we start applying the future, and then we have a allegedly better forecast of what might happen in the future. And the second component that I think it's still a bit technical, but is important to mention, is the climate shock. So our storylines are based on a physical weather shock or climatic shock. So we basically take a year in the future, we select this point, and then we try to find in the surrounding 30 years what is the largest shock that we see. And then after the shock, we try to measure what is the spike in prices or the reduction in consumption all over the supply chain. So it is a bit, we have to do a bit of like, we take from one year and put in the other, but the idea is really to add those two components and see how a shock can affect in the future. So what would be the exposure of the supply chain to large events in the future. And so we actually, in the project, we use different time periods, different GCMs, different RCPs and everything, but I think for the sake of this presentation, it would be better if I show just one time period, one model, and then just RCPs, just for the sake of simplicity. So the results won't be robust, but that's not the intention. The intention is just to show how it works. And yes, so besides the physical part, we have also the socioeconomical scenarios, and those are divided in three. So the first one is the default, that it's basically a SSP2, middle of the road, and there we are just exploring the physical shocks and seeing how it happens. But then we have two extra policies that we are calling. So the second one is, what if in Europe by 2050, 50% of the meat is not consumed? So let's assume a dietary change. And then the third scenario is, what if we don't have deforestation in Brazil, which is the main soybean producer and also the main exporter to the EU? So what if we introduce a hardcore policy where nothing that comes from the, well, allegedly or so-called considered rainforests, nothing can come from there? So what would be the effects? So we, just to catch it up, we explore both physical constraints or scenarios, but also socioeconomical scenarios. Yeah, so first, to show the results, we focus first on the producing regions and the weather shocks. And here, what we can see is that, so first, on the first figure on the top right here, we see that Argentina is the country that is most affected by the weather shocks. Then we have Brazil with a bit less, and then we have the US with slightly increased shocks. But then when you look at the production, because the production in Brazil and the US is both higher than Argentina, actually the impact that it has on the supply chain is different. But most importantly, and I hope you guys can see this well, specifically for this scenario that we chose, we have a compensation between Argentina and Brazil for the two RCPs that we are considering. So for the 2.6, Brazil has a big shock, and for the 8.5, Argentina has a big shock. And again, this is intentional. We're not running across a lot of GCMs and a lot of RCPs. It's just for the presentation. I want to take those through because the results can be very interesting following. And okay, then with those shocks in those regions, we look at the bilateral flow. So how those shocks affect Europe. And again, we see in the first figure on the top that actually the country that the EU imports the most from is Brazil. And even though the US has such as large as a production as in Brazil, it consumes most of its production. So actually the exposure from the EU perspective lies on Brazil. And then when we look at the 2.6 scenario, again, if you recall from the previous figure, it's in the 2.6 that we have a big dip in Brazil case, and in the 8.5 is Argentina. So again, the compensation that we saw before is still here. But now we have two additional socioeconomic policies, one being the diet change one, and the other the no deforestation. And for the no deforestation, so the orange line bar here in the middle, we see how important the no deforestation scenario is for the storylines, because once you don't have as much production or imports from Brazil to the EU, then if there's a shock there, it's not as relevant as it was before. So, and for the dietary change, it's a bit, you see a bit of reduction between the green and the blue bars, but it's not as relevant as we see for the no deforestation. So finally, to try to finalize it very quickly, we have the socioeconomic impacts in the EU. And what we see is, so we have 4 graphs, and I'd like first to call the attention between the bars and the dashed lines. So the dashed lines are the historical failures, or the historical impacts, and the bars are the future ones. And we see that in most cases, besides those 2 here on the bottom, everything is worse. So all the impacts are magnified. So we have higher price increases, we have higher shocks on human consumption of soybeans, and then, as I explained before, soybeans are usually used for meat consumption, so then the meat consumption also suffers from increased impacts. So this is the first point, like the future risk apparently is increasing. The second point, looking at the policies, we see that the no deforestation reduces all the impacts. And this is mostly because, as we saw before, being Brazil the most important country for the EU in terms of soy exports, once you decrease these exports, you have to compensate it somewhere else. And the model starts compensating in different countries, such as in Asia, which would not suffer from this type of shock. So therefore, all the shocks in prices and consumption, they are not so intense as it would be in the default scenario. And finally, we have the dietary change, which is the blue bars, and then we see that it's mostly affecting the lower cases here that are the meat consumption. So obviously, once you reduce the meat consumption, you reduce, the entire market is reduced, and then any shock there is gonna be more pronounced. And just to summarize everything, the presentation was really like a type of prototype of our project right now, so we showed just a handpick of scenarios. And the idea was to show that shocks in the supply chain that is very interconnected between one continent to another can be very sensitive to the entire supply chain of soybeans. Especially that we saw that if shocks happen in Brazil and Argentina, they're going to affect the EU as it is right now. But it's also important to check for regional impact. So as I showed in one of the first results, we have scenarios where Brazil is worse, others that Argentina is worse, and it's important to assess those in a more robust way. And finally, from a socioeconomic scenario perspective, what I see is that the no deforestation is highly impactful in Brazil, and therefore, because of its dependence to the EU, it will also affect the EU. But on the other hand, the dietary policy is not as important or is not as significant in terms of soybean consumption and imports, but it does affect the meat consumption a lot. And that's it. I hope you guys could understand, follow everything. And yeah, thank you.
Are there any questions?
Sorry. I was a bit confused that the slide you showed where the option where you had the changes in meat consumption, it seemed to have a stronger shock. I didn't quite understand that.
If we can come back to the slides, I can. 1 second. Maybe I can go back. Okay, then I can go on my own. 1 second. And one more? Yes, okay. So the question is regarding why those dips are larger. Yeah, basically the pool, so like, because the total numbers are much smaller in the dietary, like we have the total amount of meat consumption and soybean consumption being reduced, any variation there is going to be proportionally higher. So the shock there is going to be like, yeah, proportionally higher just because of this. But I thought of adding also like absolute numbers to show the comparison, but then you saw it was already a lot of numbers and tables, so I was okay, maybe I just let it be like this. Yeah.
Can I be next? Yes, so my name is Stefan Fronzek from the Finnish Environment Institute. Thank you for the presentation, a very nice topic and a very nice presentation. I actually have 3 little questions. One is kind of, can you shortly explain what is a storyline, what is a scenario, and you're using scenarios to create a storyline, so like what's the flow and what's the logic there? Yeah. And the second question is about the deforestation. If I saw this one figure right, I think that implied that there was a sharp decrease in imports to the EU, and I don't quite understand how that actually happens. And the third question, I cannot remember. Only 2 questions then.
Okay. So it is true, like we are using both like the storylines and the scenarios like together. So the idea of the storylines, at least in the way we're approaching this, is to make a plausible scenario or a plausible chain of events where we start in the weather shocks and we end up in a socioeconomic impact somewhere else. So specifically, we don't look like we had this deep neural network trained on historical data, but we don't look at the statistics of it, even though we have it. We're mostly looking at extreme events. So maybe I didn't make it that much clear, but so here, that's the storyline component enters here because we have the entire model as set. We know from beginning to end, and then we look at the historical event that I didn't focus in this presentation because of time, but we explored it. It was in 2012. There were failures in all 3 continents, in all 3 countries, and then we try to explain it from a weather point until the final impact, so we have everything disentangled, and then we try to reproduce this in the future, looking at those years where we select based on the yield shock. So actually, what I'm showing here was mostly like the impacts of the scenarios on the storyline, but we have as a final product for each of those analogs, we can map from the weather conditions in the Americas. Let's say in 2050, we have the weather conditions that together lead to a shock, into a soybean shock, and then those lead to those consequences like price hikes and soybean consumption reduction. So this would be the storyline, and then the scenarios are just different ways that we are setting up this storyline. So in my point of view, the storyline, as, I don't know, Ted would define, is more on the physical side, and then we add the socioeconomic policies on top to give different flavors of the storyline. And the second question I forgot. Oh yeah, true, sorry. So the deforestation is basically, we have a map, like a mask, a spatial mask on Brazil, where part of Amazon and like the Pantanal region and the central Brazil is considered tropical forest, tropical rainforest. And with this scenario, nothing in those tiles can be used as soybean exports to the EU, which is interesting because it's also a very important region for soybean production. So in the end, when we cut all that region from the soybean imports to the EU and here, that's why we have in the top figure there such a small value of imports, because basically 60% of the soybean production of Brazil is not going to the EU anymore. So and then obviously all the shocks are going to be reduced because your total value is smaller, so your absolute change is going to be smaller as well. Does it make sense? Yeah.
Yeah. Any other questions? Yeah, sorry.
Thank you. I was going to ask the same about the deforestation. Is only applied on Brazil. Maybe that's the reason it benefits Argentina. And also I know that Brazil has a long story with Globiome, and I wanted to know if you use this version of Globiome or the original, and if you use the original, have you compared to results from that version? Because I know they've included double cropping that may be important in some regions, at least in Argentina. Thank you.
Yeah, exactly. Thank you for the question. Very detailed. Yeah, so we use the global version of Globiome, so the vanilla. We're aware of the Brazilian Globiome, but we haven't tested it yet. I don't know, it could be an option. Actually, Esther is our genius behind Globiome here, so I don't know, it depends on her desire on how to move forward on this. But yeah, it could be an interesting, well, Globiome Brazil is more detailed, has the double cropping is something that also for soybeans has been shown to be, relevant. So it could be, but honestly, I don't see this happening right now, but there's always an opportunity. Yeah, I don't know if Esther wants to say anything. No? Cool.
So I hope, I don't know if you're well connected with them. I know Aline Sotteroni, who is the mastermind, actually left, so I lost my contact with the Brazilians. Okay, so happy to talk about it further. So it's also applied on Argentina, but there's much less deforestation there and much less soybean expansion as predicted in Globiome, at least in the default version, from forest areas in the future. So that's why you wouldn't see the effect so much in Argentina, but it is applied.
Okay, I just got one last question online. It's from Marina. Could you expand on the relationship between meat consumption and shock?
I think that was already answered in the first question. It was the same, so thank you.
Yeah, no problems.
Yeah.
Okay, then we'll go on to the next presentation. Thank you.
Okay, thank you. So my talk today is about applying, embedding physical climate storylines into causal networks. It's ongoing work with colleagues, and it's part of the RECEIT project introduced at the beginning. So I'll introduce how this could be useful, what we could gain from this, and I'll introduce an explicit example, but I won't go into quantitative results. Rather, I'll focus on the methodological aspects of this. So starting with what causal networks are. Causal networks are directed acyclic graphs with the conditional probabilistic dependencies of the system represented in the graph structure, as in the one you see on the screen. So the graph consists of nodes that correspond to elements within the storyline, and the nodes are assigned probabilistic values that are conditional upon the parent node. So these DAGs that have probabilities assigned are typically called Bayesian networks. Causal networks are special types of Bayesian networks in the sense that the connections between the nodes represent causal relationships, not mere observational correlations. So if an intervention is done in the parent node element, or the value changes with time, then it directly affects the child node element. So we want to use this causal network to answer inference queries regarding the storyline. And this can be done because probabilistic values are assigned to the causal network based on data and beliefs of the storyline. Okay, the reason we want to combine physical climate storylines with causal networks comes from the fact that both have this conditioning nature. So as I said, causal networks are conditional, are assigned conditional probabilities, whereas whereas climate storylines are analyzed based on a given climate event or a given climate condition. So the analysis is conditional on those events. So by mapping those elements and mapping the elements downstream, we can use the causal network as a tool to analyze the climate storyline. Okay, going further a bit deeper into why we want to use causal networks, what we could gain from this. The main point is that it allows us to incorporate the uncertainties of the climate storyline as probabilities of the causal network. So these uncertainties can, starting from the bottom, could be aleatoric processes within the climate storyline, but they could also be epistemic uncertainties, what we don't know about the storyline. And the probabilities of the corresponding to the uncertainties can be assigned by expert analyses, but they could also be assigned, and this will be some focus of my talk today, by users using the causal network. We have stakeholders and policymakers in mind here, but user expectations can go into the causal network as probabilities giving user-tailored policy prescriptions coming from the causal networks. We'll see this in an example later. Another reason we might want to use causal networks is that, as I said, these represent causal relationships, so the causal structure of the storyline becomes apparent in the network. So they can, causal networks can be used as an interface to explore the storyline with stakeholders and policymakers. So it can be used in sensitivity analyses led by stakeholders, and also to investigate possible policy options that could enter the storyline, and by using causal networks with stakeholders and policymakers. Okay, so all that was a bit abstract, but I'll go into an explicit example and see how those elements come in. The storyline I introduced here is about the EU Solidarity Fund and tropical cyclones. So this storyline was introduced in Gular et al. 2021. So the EU Solidarity Fund is an emergency fund that pays out when damages are caused in EU nations. Now, EU nations have islands outside Europe, say in the Caribbean or the Indian Ocean. So when tropical cyclones hit those areas and cause damages, then the EU Solidarity Fund comes in to pay out for the damages caused. And what we're interested in here is to consider a specific storyline of tropical cyclones causing damages, and then seeing whether that could be of concern for the European Union Solidarity Fund, whether the capital of the fund could become negative as a result of the damages caused. So in the Gular et al. Paper, they considered downward counterfactual cyclones of historical cyclones created in 2017, historical cyclones that occurred in 2017 and 2018, 13 in total. Downward counterfactual as in what if situations that could have happened based on the past forecasts. So on the right, you see a figure of this. So the blue solid line corresponds to the actual trajectory of a cyclone that occurred in 2017. It goes over Madagascar. But based on past forecasts, it could have gone over the dotted trajectory on the right. And on the trajectory, there's an EU island. I think it was an island of France. And this could have caused much damage on that island, leading to payouts from the Solidarity Fund. So considering these kinds of downward counterfactual cyclones of the 13 historical cyclones that occurred, we consider what could have happened to in the 13 cyclones. But we have 13 cyclones, but thinking of a situation where all 13 cyclones cause damages with downward counterfactual situations is not realistic. So we consider subsets of the cyclone and think of each subset as individual storylines. Okay, so in the next slide, I'll show the causal network embedding this storyline, but just stepping back a bit, I'd like to go through the general method of implementing embedding storylines into causal networks. So what we want to do first is to create a causal network corresponding to the storyline elements and realizing the causal structure of the storyline. And in this case, we want to enable the conditioning on the specific sets of cyclones. So we're going to prepare 13 nodes corresponding to each cyclone. And then after that, we assign conditional probabilities based on the simulated downward counterfactuals and give probabilistic values to each of them. So, and the probabilities would be conditional on the different climate and socioeconomic expectations, meaning that in future climates, the cyclones would become stronger, so they would cause much damage, and that should be accounted for and assigned as probabilities. The explicit values would be assigned. And also socioeconomic expectation means that more GDP increase in the island would lead to larger damages, so that should also be assigned. And also the last point, policy options, meaning that we're interested in the EU Solidarity Fund, and EU nations could invest in the EU Solidarity Fund so that it won't go into deficit. So that's another policy option. And all these elements go in as nodes in the causal network. So these two steps with these two steps, causal network corresponding to the storyline would be generated, and we could ask the causal network to give predictions about the EU Solidarity Fund capital given a specific storyline, that it is the specific set of cyclones. Okay, so the causal network corresponding to the storyline I just introduced would look like this. So we have 13 cyclones in this big causal network. Sorry, on the screen it's a bit, it's disappeared, but we have 13 cyclones. The ones not chosen are grayed out. So here we have 5 cyclones chosen within the storyline. So this is a storyline that includes 5 storylines, 5 cyclones. And on the left, we have the first year corresponding to 2017, and on the right, we have the second year corresponding to 2018. And cyclones lead to some hazard level, and the hazard level gives a payout, determines the amount of payout in a given year, and the payout determines how much capital is left in the EU Solidarity Fund. Now, in the red part, we have nodes that the user of this causal network can assign values to. So starting from the center, we have hazard increase. So that is how much the cyclone intensity would increase in a future climate, and that would affect how much hazard is created in a given year. After that, on the left to the hazard increase, we have GDP increase corresponding to how much GDP increase there would be in the future, and that would lead to payout. Sorry, that would result in larger damage caused in the islands and larger payout values. And finally, the capital is determined by the payout values and how much capital increase is made by policy. So these values determine how the outcome of the capital at the very bottom. Now, the user can assign probabilistic values on the GDP increase and hazard increase, depending on what they think the future would, what kind of future would realize. So if they think climate change is going to be very severe due to huge emissions, they could place a probability distribution corresponding to that. And these could, in principle, be related to the climate scenarios, SSBs and RCB scenarios. Okay, so what we have in mind is to use this kind of causal network as a tool where, as an interactive tool where the user can assign probabilities to the square nodes and give user-tailored predictions for the outcomes. So we created a user interface using an R package called Shiny, where that could be done. So on the right, you see the causal network you just saw, and on the left, you see a panel where the user, we have stakeholders and policymakers in mind, could choose the specific cyclones that enter the storyline. We have the same cyclones here. And where the user can also assign a probabilistic distribution over the GDP increase and the hazard intensity increase. So these correspond to the socioeconomic future and the climate change future, and what the user inputs these based on what the user expects about the future. The user could also choose a specific policy option, how much capital increase they want for the EU Solidarity Fund, and that the causal network with these inputs creates a probability distribution output that shows how much capital would be left in the Solidarity Fund in a given year. So the blue part shows the capital will remain positive, and the red part shows that the capital will go negative, go in deficit. And the user can use this kind of probability distribution to make policy decisions. So what I just showed is how user expectations can be incorporated into the causal network as Bayesian priors to give probability distributions on the remaining capital. Actually, when we think of what the user, policymaker, or stakeholder might want to do is to compare several distributions based on what capital increase policy options they choose. So actually, we can make this a workflow, and so on the right, you see two distributions based on different choices by the user, different capital increase values. On the left is a small a distribution you get when you have a smaller capital increase. On the right, you have a capital increase probability distribution when you have a larger capital increase. And the user can compare these two and make a decision, but rather we could also make the user choose some risk averseness. So if the user is risk neutral, the user might want to choose a policy that just gives a policy positive value on average, a positive capital remaining on average. So the user would choose the capital increase value on the left, and if the user is very risk averse, they would choose a capital increase value that would lead to the distribution on the right. So, and this can be calculated using assumptions on risk averseness. So this is another window where the user held values can come in to and lead, the user can choose their risk averseness, and actually in the interface we have the interface outputs what policy decisions the user should make based on the risk averseness they have by going through using the causal network several times. Okay, so that's all I have. To summarize, the storyline is, by embedding the storyline into causal networks, this can be used as an interface to incorporate the user's user-held values. So the user's expectations on futures came in as their expectations on the climate change future and socioeconomic assumptions, GDP increase. These could be related to SPRCP scenarios, and these led to a probability distribution that's tailored to the user expectations. And the policy options the user should take could also be tailored according to the user's risk averseness. Okay, that's all. Thank you.
Okay, it's over to you, Marina.
No, are there any questions for Taro?
Yes?
Yeah, thanks a lot for the very interesting presentation. So I can see the value of it as a tool, right, for stakeholders to define also where they should maybe invest in, and but I'm not quite sure if if I understand the flow and where it's coming from, because I can understand that in the squared boxes you have the stakeholders deciding. Then it trickles down in the rounds, right? So, but what sort of like is the method behind deciding how this propagates eventually into the eventual impacts?
So, thank you. So what's behind this in the first place is that we have an impact model that comes from the storyline. And what the impact model itself is, the results from the impact model is embedded within this causal network. So the causal network sort of uses the results from the impact model.
Impact model for basically a lot of iterations, as many as potentially can be chosen by the stakeholder, right? So in this sense, it's mostly to visualize actually the impact.
Yes. At this level, yes. Doesn't necessarily have to be all. Here we're going through every possible situation, but if it's continuous, it doesn't have to be necessarily have to be everything. Yes.
Okay, thanks.
Thank you. So a quick question on if I understood correctly, part of the storyline that users can select is selecting some of these 13 cyclones, but are these kind of 13 cyclones that have actually happened within this 2-year period? So there's no storyline that could actually show an increase in the number of cyclones or their severity, or would that be possible with your tool also?
So, thank you. So, for the severity increases, that could be directly incorporated as the hazard different values for the hazard increase node on the top. The frequency increases at this level should be, so we're in this storyline approach, we're specifying the which cyclones actually happen. So the frequency element doesn't directly come in. But if you want to look at a more frequent situation in the future, you can choose more cyclones and look at the specific storyline where it includes a specific set of more numbers of cyclones.
Okay, thank you.
All right, hello everyone. Well, I'll be presenting now on behalf of my colleagues our take on this storylines approach with this mouthful of title, which I won't be repeating now. I would like to start the presentation with a hypothetical scene from a day at an operation room at a large Finnish hospital on a hot summer's day during the heat wave of the summer 2018. While this description here is a hypothetical scene, it's inspired by real experiences from gathered from an interview of the hospital staff, or a survey of the hospital staff working at this Finnish hospital. And it suggests that since these are observed working conditions, that changes are needed to ensure hospital functionality under changing climate and increased risk of heat waves and extreme temperatures. And in this context, we thought that the storylines approach might aid us in identifying risks, future risks to consider, and ways in communicating those risks. The work or the broader context is set by various European and national policies, such as the European EU Strategy on Adaptation to Climate Change, Finnish National Adaptation Plan, the Finnish Ministry of the Environment's Municipal Climate Change Solutions Program, and several others. As we all know, the implications of society depend on uncertain demographic, economic, and environmental development that are affected by national, European, and global developments. And since these developments can't be assessed with certainty, then there's a need for scenarios and narratives. And we now here explore the storylines, and these are developed in our project together with extending global shared socioeconomic pathways to the regional scale and developing regionalized climate projections. And the aim of the storylines component is to assess whether storylines can offer a way of communicating climate impacts and risks that is meaningful for communities and decision makers, highlighting issues that may inform necessary adaptation responses. The work is conducted in this project called Finscapes, Finnish Scenarios for Climate Change Research, Addressing Policies, Regions and Integrated Systems. And it was launched in February 2021 with a central aim of co-creating with local experts and stakeholders a set of integrated scenarios of future climate and socioeconomic development at the regional scale in Finland. And the main part of the project is dedicated to developing these regional, what on earth? SSPs, but I will not be focusing on those in my talk, but they provide the sort of context for the work, because we might be then using those SSPs that are developed in the project later on to inform the storylines work at a later stage. In the project, it was decided to focus the work based on stakeholder discussions on these two regions in Finland, North Karelia in the eastern part of Finland, and 3 neighboring Ostrobotnian countries in the western part of Finland. And in the stakeholder discussions, these region-relevant systems were identified, and the SSP work is now continuing on these systems. And this has a life of its own, this presentation. Well, anyway, the storylines work then decided to focus on these same 2 sectors that were chosen in the project. And we decided to start working on developing storylines for the health system for the South Ostrobotnia, looking at a specific case, and then more broadly for the dairy industry in North Karelia. Well, firstly, before I go into the main content of my talk, it's quite useful to distinguish between the different kinds of storylines. Most of this session is, of course, dedicated to looking at the physical climate storylines that focus on the climate. I'm not going to say much about those, but I'm focusing here now on the climate impact storylines, where the work starts from a slightly different perspective, starting from the impact, firstly identifying a notable impact of interest, and then looking how different climate and socioeconomic changes affect the impact, looking at possibly acute impacts brought about climate-related events that could possibly occur in the future, but have not yet been observed, or possibly also like potentially beneficial impacts. The approach that we've been trying to now formalize starts with a stakeholder and expert dialogue, taking into multiple different viewpoints. And based on those discussions, a notable climate impact is identified. And to be able to understand that climate factors that are triggering the impact need to be considered, different exposure and vulnerability factors that then predispose the system or sector of interest need to also be considered. And after that, then the magnitude and frequency of these notable climate impacts can be assessed, firstly from the historical data, looking at observations and documentations, and then also looking at future data based on also, not future data, but using models to look at how the impact might change in the future, or indicators in the lack of models, or then expert judgments. Then next, response options need to be considered that take into account various aspects of adaptation, resilience, and those then reviewed also with the models possibly to see how they help in ameliorating the effects of the impact. And then in the end, a number of climate impact storylines can be developed that reflect then different perspectives that are chosen for the storyline work. In the project as a whole, there will be developed these SSP narratives, and some of the variables might be quantified. There is also work on developing regional climate projections from the CMIP6 projections, and that is also has already progressed quite a bit. And there is then also provision in the project to create visualizations of the 4 SSP futures. And also then bring all these different aspects together to produce regional narratives and kind of a picture of the situation. And how the storylines feeds into this is kind of focusing on a more specific impact, and instead of the broader descriptions that these SSP narratives and these regional climate projections give for the region, focus on a very regional example. And there's this quote that quite nicely summarizes our way of thinking about this, that storylines aim to set a specific train of thought in motion, communicating why an issue might be a problem, who or what might be responsible for it, and what should be done about it. I will now give a quick look to the health example that we're working on, we just started working on. This is the Seinäjoki Central Hospital that provides the setting for the storylines approach in the health sector. It was originally built in the 1970s and expanded in 2007 and 2018 with new sections added in 2012. And the hospital's facilities have been systematically, no such animation here, well fine, renovated since 2009. The hospital district of South Ostrobothnia encompasses 18 municipalities in South Ostrobothnia with a total population of almost 190,000 people. The hospital provides medical care for emergency patients around the clock and also non-urgent medical care in all key specialties. They have identified in the hospital various current problems with the hospital. It is spread out over a large area, causing long distances between key functionalities that should be located close to each other. Some of the buildings are approaching the end of their life cycle, and some of the buildings have not yet been refurbished. Low ceiling height in some of the old buildings make it difficult to install modern air conditioning. And then there are various accessibility issues. The hospital is located on a high hill, making access difficult by foot or bicycle, especially with the elderly. And it's also only serviced by one bus line that runs approximately once every hour. And there is inadequate space for recycling waste. As a result, the hospital district of South Ostrobothnia launched this project called Hospital 2040. And the aim of the project is to develop the Seinäjoki Central Hospital in a customer-oriented, renovated and resource-efficient hospital. The project started in early 2020 and is exploring and comparing future options for the hospital area. It aims to draw up conceptual plans for the various investment options for the activities and their cost implications for decision making. And they look at various different perspectives, from refurbishing to building a whole new hospital in a totally new area. And in this project, they also have to consider expected socioeconomic changes as well as climate changes, such as expected demographic changes in the area. For example, 1 in 3 is expected to be over 65 by 2040 in the region. Population is declining even by 30% in some of the municipalities. As a result of the demographic changes, new areas being built around the hospital, there are changes to be expected in the traffic flows and mobility. There are changes that are happening rapidly in digitalization and challenges in attracting qualified personnel. Changes are expected in the spectrum of diseases that they have to deal with in the hospital, new diseases, increase in dementia, etc. And in the lack of a crystal ball, the Hospital 2040 project approached our project with the aim of wanting to apply the storylines work in their planning of how they would be renovating or building a new hospital. So there is a concrete need for this work that we're doing in this project. There's a recent master's thesis written by one of the stakeholders in the project, who also works at the Hospital 2040 project, that assessed the functionality of different aged buildings in Seinäjoki Central Hospital during heat waves in summers 2018 and 19, looking at humidity and heat heat issues through user perspectives. And based on the discussions with the Hospital 2040 project, 3 viewpoints for the storyline work were identified. Firstly, experts of building services or technical solutions and support services, maintenance and preparedness were the main focus in this viewpoint. Secondly, medical staff, including doctors, looking at specifically occupational health. And thirdly, patients, clients, with a focus on amount of care and treatment required and the spectrum of diseases that are needed to be treated. So if we now play out through this example with a simplified example of what might be the building blocks for this approach. So the stakeholder dialogue could suggest that heat waves will increase the risk of, or the morbidity and mortality of elderly people. And the first step might be to explore the observed climate, to look at how the temperature has evolved in the past, then look at future projections and see what it might look like in the future. Look at population projections, how the population might be changing in the area, how it might look like. And there might be estimations of the trends in the different diseases, how they might be developing. And these together would all inform the analysis of the increase in heat-related morbidity and mortality. Then models or indicators or expert judgment could be applied to look at how this might develop in the future, also look at how often it has happened in the future, how it has looked like in the past. And then different adaptation options and such could be assessed and looked how they then affect the development of morbidity or mortality under the heat wave that is looked into. And then as a result, the different perspectives would all have different, sort of slightly different storylines that describe how this impact would look like from their perspective. And then at a later stage, we might also look at how these might look like under different SSP futures, but that wouldn't be necessarily the starting point for the work, but we still need to slightly think about how we would include this in the work. And so next we will start developing these storylines in close contact with the stakeholders for both the health and the dairy case, and following the steps of the approach. And alongside this then happens the development of the regional climate projections and the SSP narratives in other parts of the project. And at a later stage, there will be an examination of the utility of regional climate and impact storylines among a diverse range of stakeholders, both within and outside the 2 study regions, to judge their value and effectiveness. Thank you.
Okay, questions?
Hi, thanks for the interesting presentations. Always like to see these very detailed case studies, so very useful. I have 2, I guess, related questions. I think the second to last slide, I think you were indicating that you also plan to prepare regional, subnational projections, population projections. So my question is, I guess, how are you planning to do this? Because we know that the SSP drivers are only available at the national level. And secondly, I think you, I guess, in the future plan to do some modeling to assess the impact of climate change. Just curious to know what kind of models you plan to use for this very detailed sectoral approach.
Yes, very important points. Well, this was mainly at this stage more of a not really a hypothetical, but an example of what sort of aspects we could be looking into. There are some population projections existing for Finland already that have been developed in other projects. We are not necessarily looking into developing them in this project, but the SSP part might go in further into this, but it's not necessarily what I will be working with. So, but I think we would at this stage be applying what already exists in the Finnish context. And then the modeling, yes, of course, it depends on what we then in the end decide to choose with the stakeholders and what impact we would be focusing on. We haven't yet gone that far. We're in discussion with the hospital, but we still need to look at that. So it depends, of course, on the availability of the models. There are models for looking at the morbidity and mortality. Colleagues of ours, us working at the Finnish Meteorological Institute, are applying such models, but it might not be the impact that we're focusing on, so it remains to be seen if it's possible to do some modeling. But we're not going to start developing models of our own in this project.
Thank you.
Yep, one more question.
Hi, Ted Shepard. You said you weren't going to look at the physical climate storylines, but it seems it would be so easy to do from where you are. And so are you thinking about that?
Yeah, I might have missed something that I needed to say, that other colleagues in the project from the Finnish Meteorological Institute, I mean, they are also working on developing the physical climate storylines, but the part that I now wanted to present here focused on the kind of the reverse sort of way looking at the things, starting from the impact. But yes, we are also looking into those.
Okay, any other questions? Nope, okay, we're ready for the next presentation. Thank you.
Okay, so so there's so the title was not just so stories, which I'll explain when I get there. So as you probably know, climate scientists tend to describe changes in extreme events probabilistically. This is a figure from the Working Group 1 AR6 summary for policymakers for temperature extremes and heavy precipitation over land. Of course, to do that, you have to aggregate. And at the regional scale, when you look at this classical, what I could call a classical approach, there's challenges from uncertainty in model projections, and then also lack of verifying data. And this is just another figure from the SPM, which shows that in parts of the world, the models don't agree on the sign of change. And in many parts of the world, and especially in the global south, there's limited data and literature, so there's a real problem there. And even when aggregation is reliable, it's not informative about individual cases. This is a famous example, which seems to me quite apropos, since I suspect when this place was in its prime, there were probably a lot of cavalry units around as well. So this is from Borkowitz in 1898 for the Prussian army, and looked at the number of Prussian cavalry units suffering at the death of a soldier by horse kick in any given year. Follows a beautiful Poisson distribution, shows that the deaths happened by chance. But I suspect if you were the commanding officer of a unit and the parent of one of the soldiers that died came to you and asked what happened, you wouldn't just say it was bad luck. You would think of all the things that you might have done that might have made it not happen. Every event has a tragic story behind it. So even though it's true there's a probability distribution, it doesn't really mean it depends on your way of looking at it. And I think this dialectic between aggregate and individual occurs in many disciplines. It occurs, for example, between public health and clinical health, and it applies everywhere. And it's because events in the real world are not independent and identically distributed. It's only a model. So I've been looking at storylines, of course, and this relates to a concept of narrative in science, and actually that has a long history, and it's especially being used in evolutionary biology. And this is a quote from, I apologize for the long quote, from Stephen Jay Gould, the famous evolutionary biologist. He said, natural historians have too often been apologetic, but most emphatically should not be, in supporting a plurality of legitimately scientific modes, including a narrative or historical style that explicitly links the explanation of outcomes not only to spatio-temporally invariant laws of nature. And I highlight that because as a physicist by training, that's what physicists are used to doing, spatio-temporally invariant laws of nature, and not to think about contingencies. But he's arguing you should also think of the explanation as involving specific contingencies of antecedent states, which, if constituted differently, could not have generated the observed result. So I've been working with, as Marina said, I've been working with philosophers of science, especially with Lisa Lloyd, and this is a paper from a special issue in climatic change, and we asked about narrative was one of the things that we linked to. And this is an example of an extreme event from a year ago in Nepal. It was a debris outflow. This is an image from space of a valley in Nepal, and it was heavy monsoon rainfall, but it was a rain on snow event, and it led to a whole cascading set of failures with various natural dams that had been formed by previous outflows, just a whole set of events based on contingencies, and this agriculture area is gone. It's buried knee deep in debris. Don't think they're getting that farmland back. So these kind of singular events are happening more and more. So why shouldn't we think about narratives too? But Gould, with his colleague Lewontin, had earlier cautioned against untestable just so stories. And for those who don't have a British background, Rudyard Kipling was a novelist, and he wrote Jungle Book and so on. But this was just so stories with things like how the leopard got its spots and that kind of thing. So this is used as a derisive phrase, and Gould and Lewontin did argue that you have to be you can't just use consistency with natural selection as a sole criterion, because plausible stories can always be told. So you need to have an answer to this, and I think the answer is actually in probability theory. And I refer a lot to Jeffreys, who was a geophysicist, and his theory of probability. Another long quotation, but a really beautiful text, I think. He says, we get no evidence for a hypothesis by merely working out its consequences and showing they agree with some observations, because it may happen that a wide range of other hypotheses would agree with those observations equally well. To get evidence for it, we must also examine its various contradictories and show they do not fit the observations, which you might call Sherlock Holmes principle. I think you'd agree it's just common sense. And this is all in Bayesian reasoning. So storylines can be representative of scientific hypothesis. We have a hypothesis we call H with the data D, and the consistency of that hypothesis with the data is the probability of the data given the hypothesis. In the case of the null, this is the p-value. It's just the likelihood function in general. Of course, you need a well-defined hypothesis. But what we're actually interested in is whether the data supports the hypothesis. We're interested in the probability of the hypothesis given that data. And so to do that, to figure that out, we just use Bayes' theorem, which is shown here, and you need to basically go from the likelihood function to the support for the hypothesis. And there's two factors there, P of H and P of D, that come up. So P of H is the probability of the hypothesis before you've looked at the data, known as the prior hypothesis, or prior probability. So that's the relevance of prior knowledge. It encodes the aphorism that strong claims require strong evidence. Again, common sense, but it's built into Bayesian reasoning. And then P of D is a little more subtle, but that's the one that requires all the possible explanations for the data. In other words, was this data a really strange thing, or was it something that actually wasn't that surprising? And so formally you write not H, this little hockey stick symbol, as the negation or complement of H. It could include several explanations. And then you just, from the axioms of probability, P of D is just the sum of P of D given H times P of H plus P of D given not H times P of H, P of not H. It's trivial, really. It's very, very basic. But nowhere in any climate science publication have I ever seen P of H or P of D discussed when people go from the p-value to the probability of H given D. It's just remarkable. This is not, of course, just climate science. This is across all of science. It's been widely talked about. So I've discussed this in an essay in another issue of climate change, which actually Marina edited from a workshop that she organized. So it's convenient to work with what's known as the odds form of Bayes' theorem, which is just the probability of the hypothesis over the probability of not the hypothesis, the odds of the hypothesis. And you see that to go from the prior on the right in yellow to the what's called the posterior on the left, you need this ratio known as the Bayes factor. The Bayes factor is just the odds of the hypothesis, but to compute that, you need a well-defined alternative hypothesis. You can't just go fishing with a vaguely specified alternative hypothesis. You need to consider all the plausible explanations. That's what I'm going to talk about. Now, there's two kinds of physical climate storylines that have been mainly used in the literature. One is what are sometimes now called dynamical storylines based on remote drivers, with for example, the paper with Giuseppe Zappa from 5 years ago. in that case, it's rather clear because you're looking at all the different, at least for the CMIP models, you're looking at everything. But the event storylines are the one which I think we're mainly talking about here. So it's not obvious how you would do that. So with Lisa Lloyd, we've actually looked at the way that liability is established in what's known as tort law, which is damages. And so we found that this is quite useful. So this is another paper that with Lisa. So the first, this is the 5 steps of causality in tort law. So the first is just a link between the exposure to risk and the bad outcomes, which has a causal explanation, which is pretty straightforward normally. Second, though, I highlight you need a complete set of plausible explanations or conditioning properties for the bad outcomes. You should look at tests that could discriminate between the different explanations, and you should draw on all relevant information, including scientific committees and things like, for example, IPCC. So it's all there. And then the fifth step is you have to show the bad outcomes more probable with the accountable cause than without it. So you're actually saying, is the risk ratio greater than 1? So the risk ratio for an event attribution, it's just the Bayes factor. And in this National Academy's report on extreme event attribution that Marina referred to in her introduction, this equation was shown, very simple equation, just based on the axioms of probability. You say, what's the probability under, let's say, F, which could be factual, so that's, say, with climate change. If you're doing an attribution, C is the counterfactual, that's without climate change. So it's just the risk ratio of the joint occurrence of the event that you're worried about, and C is the atmospheric circulation situation conducive to that event. So for a heat wave, it would be typically a blocking situation, and that just factorizes the conditional probability P of the event given the circulation times the probability of the circulation. The first factor there is what you might call the primary hypothesis, which is the thermodynamic aspects of climate change. That would be the increase in certainly in temperature given the circulation, perhaps the change in the precipitation too. And then the second factor is the aspects of climate change that are not included, which, for example, in Enrique's case, he was keying around a La Nina event, and he was basically looking at the conditional probability given that La Nina event. He didn't look at the likelihood of La Nina changing. We don't trust CMIP for that anyway. So just to repeat that equation, the thing is that the first factor is greater than unity, which it would typically be in these extreme event attribution or in these event storylines. In order for climate change to not increase the probability of the event, you need to be able to argue the second factor was strong enough to overcome the first. And I think that's it would be a very difficult case to make, given the uncertainties, well-known uncertainties concerning the dynamical response to climate change and the lack of any agreed-upon theories. If you didn't know anything else, a Bayesian approach would just introduce an uncertainty for that, which would be a uniform distribution centered around zero change. So to make clear, some people feel that the storyline approach is a biased estimator of risk, because it's saying things like you always find you always blame climate change. Well, it's not a biased estimator. If you really don't know anything about the circulation change, it's an unbiased estimator. And the standard of scientific accuracy in tort law context is much lower, and it could be, for example, for decision makers too, is based on the preponderance of evidence. In other words, more likely than not, which is much lower than the 95% confidence level that we tend to use in climate science. So as Taro emphasized, the risk tolerance should be determined by the user based on their context. We shouldn't just be imposing this 95% confidence. So storyline event of attribution is not a just so story. And it's been, of course, our argument about, so a lot of it's about statistics, and it's been argued for many years now that we should get rid of the concept of statistical significance. This is an editorial from Nature 3 years ago. Climate change science is anchored in physical understanding. I think everyone would agree, but yet it's the case, and I know this from bitter experience, that frequentist practices and null hypothesis significance testing absolutely dominate published climate change science. And this leads to a lack of logical rigor, and I outlined several of those in that paper on statistical practice. So I think, frankly speaking, properly done, there's far more rigor in narrative storyline reasoning than there is in probabilistic approaches. And just to give an example, this is with Regina Rodriguez, a colleague of mine in Brazil, and we published a perspective in PNAS Nexus in the inaugural issue, and we used as a case study a compound extreme event in southeast Brazil. It was a failure of the monsoon in the summer of 2013-2014. You can see the upper left, the climatological situation is the South Atlantic convergence zone leads to a flow of moisture from the Amazon, but there was a blocking anticyclone, led to precipitation anomaly, dry conditions, also because of the clear skies, temperature, heat waves over land and ocean. It was a classic compound event affecting the food, water, energy nexus. There was a probabilistic event attribution of that probabilistic attribution study of that event, published in the BAM's special issue on extremes, and they found insufficient evidence that climate change increased drought risk. Their evidence is shown here. This is a risk ratio, so greater than 1 would say that climate change increased the risk, less than 1 would say it decreased it. The observations show a tendency towards increase. The CMIP models, for what they're worth, also show a tendency to increased risk, but the two versions of the Met Office model they used showed a decrease. They pooled the uncertainties. At straddle 1, they said there was no evidence, insufficient evidence. They meant to reject the null hypothesis. But you can ask insufficient for whom? Certainly if you were a manager of resources, you might be concerned, and you might not trust the UK model for some reason. So it's also a question of justice, and in this paper with Regina, we went back to Schumacher's famous Small is Beautiful book almost 50 years ago, and he asked how would economics look as if it was structured as if people mattered, and we asked how climate change science would look if it was structured as if people mattered, and we followed the Small is Beautiful philosophy. I think we saw lots and lots of connections. You have to grapple with the complexity of local situations. We just seen in the previous talk an example of that, and the way to do that is by expressing climate knowledge in a conditional form rather than just marginalizing over everything. The second is the importance of simplicity, which is when dealing with deep uncertainty, which is the use of physical climate storylines and climate impact storylines. And finally, empowering local communities to make sense of their own situation by developing what Schumacher called intermediate technologies. So those, I hope, are causal networks and the kind of thing that Tara is working on that build trust and transparency. Thank you very much.
Okay, do we have any questions? Yep.
Thank you. It was a very interesting talk. I work in mitigation, so I'm kind of always thinking about how to explain what you were talking about in the context of encouraging people to get on board with mitigation. I don't know, this last slide kind of bothered me a little bit because I always rely on climate change to be not, I don't know, I'm not against any of this, but to be sort of as objective as possible. Because then when we start to look at things like behavior change, we can point to that and say, well, that's based on physical laws and it's based on observations. I guess kind of questioning in terms of the public face of climate change and the fact that sometimes things get in the press and then there's especially things like assigning particular events to climate change. There's a huge amount of controversy. So anyway, I'm just sort of thinking how to communicate this in a way that ensures people take it seriously.
Yeah, well, that's a good. It's maybe this will be a discussion topic every time. I had an American colleague that told me, don't use that word storylines because they're dealing with a huge skeptic community over there, and he was afraid that just that word would somehow create all sorts of problems. I don't think we have a problem with the term storylines particularly. The question of subjectivity is certainly a very, very important one, but I feel there is no objectivity. I mean, it's a very contested concept, and if we bury subjectivity, that's worse. So it's better to be clear about subjectivity, and of course, IPCC uses it constantly. They just call it expert judgment. And there are processes of doing that. And as I've also tried to argue, you don't just make up a storyline, you have to test its consistency with the data that you have. So, you don't just say something. That's what if you try to compute Bayes factors and things, if you have data, you would be looking at the strength of evidence for your explanation and looking at how it stands up compared to other explanations. And in terms of extreme event attribution, I think the problem is that it's phrased as a dichotomous thing, as if it's true or false. And actually, the probabilistic approach does that too. And that's obviously wrong. I mean, it's multiple causal factors, and climate change, I think it's fair to say, is a factor. Then to say is it there or not doesn't make sense. It's a question of what sign it is and how big it is. It could be up or down, but there's some effect, we know. And there's other factors that like the local adaptation actions and that kind of thing too. And so, in fact, one of the concerns with the probabilistic approach is that now a local manager of whatever, mayor or something, can blame their impacts on climate change, when actually the fact that they may not have dealt with certain problems could be a bigger factor. So I think actually this is a more transparent, or should be, hopefully, a more transparent approach, because it allows you to draw out the multiple causal factors and talk about the strength of evidence for each of them. So yeah, it is a legitimate question, absolutely, and I think we have to find ways to communicate. Of course, if we just called it a hypothesis, a scientific hypothesis rather than a storyline, people might not have so much trouble with it. But I think I was trying to be a bit provocative with the term. So. Oh, Esther.
Thanks a lot for the interesting presentation. Maybe one quick question. So I think in the end it bottles down a little bit to the usability or the applicability also compared to a probabilistic and a storyline. So when I make my normal impact chain, averaging everything out, I know 100% that I'm incorrect and the world will not be as I portray it. And here you would be like maybe 1 in 1,000, you would be correct, right? But then still with a probabilistic setting, no, I'm not, maybe I'm in a range of possibilities or so. So my question is a bit how, even though you know maybe like you're more often correct than in the other approach, how to sell it or how to make it usable or applicable or for like stakeholders or policymakers or so.
I'll just try to keep this reasonably brief. I guess the first thing is that in the probabilistic approach, you're actually doing the same. It's all conditional statements. It's just that you marginalize over everything. But these models don't give heat waves the way that we're getting heat waves now. When people are doing these probabilistic attributions or flooding more and more, they find that the press release is that the event was impossible without climate change. What they don't tell you is that the event was impossible with climate change, which tells you that the method's wrong. CMIP models don't capture these really long, persistent circulation events. So it's sort of partly, in terms of accuracy, it's a trade-off. Do you want to have a physically realistic extreme event, and then pay the price in terms of generality, or get the statement that it doesn't even have? In fact, there's published attribution. I don't know if they're published, but anyway, announced and press released attribution studies of extreme precipitation from tropical cyclones using models that don't even have tropical cyclones. They just look at all the precipitation and they make that link with tropical cyclones. Is that helpful? It's much better. But what Tero's doing is to use a real tropical cyclone, which you can drive a realistic impact model. So I think we do have to challenge the people that are marginalizing over everything, because what they're marginalizing over probably isn't realistic. But then I'll just quickly say, you should never really just give one storyline. You should give a few, and the idea is to span the range. And if you're stress testing, you'll be probing certain parts of the tail and this kind of thing. So I think that's the answer. We have to. we do have to connect the storyline approach to probabilistic approaches, but that is exactly where the causal network framework, I think, can do it. It's probably enough for me.
Okay, I think Marina wants to say something.
Yeah, I just wanted to, we're kind of running over, so I just wanted to say a few concluding words. Like, first of all, thanks all the speakers. These have been all very interesting presentations. And I also wanted to flag that Sandra Ricard has a poster, so you can check that out. It's a virtual poster, so you can check that out on the IIASA Connect platform. The link to her poster is at the end of the program if you click on session 51 in the program. So on the session specific program. So just to conclude, like I just wanted to stress again, so earlier this morning in the plenary, I was asking a question about sort of collaboration across disciplinary expertises, but like also across the sciences and the humanities. And so the work we're doing in Receipt is interdisciplinary in that sense. I'm having the honor of working with Taro and with Ted, and I'm a philosopher of science by training. So I think about scientific methodology most of the time, and what is very interesting is that emerged from Ted's talk is that these kind of discussions need to be reconsidered, right? So it's not like we have a scientific method that we can just take for granted. We always have to bring these kinds of discussions back to the table to see whether our methods are adequate for purpose and whether we are actually achieving what we want to do. Anyways, yeah. So this is it. I wanted to thank you again, and sorry I can't be there with you. I hope you have a great rest of the forum. Bye-bye.
Thank you.